Continuity: the function f must be continuous on the closed interval a to b in plain language. You can draw the graph from a to b without lifting your pen. Differentiability: f must have a derivative at every interior point. A to b, this means the graph has no sharp corners or cusps inside the interval. Equal endpoint values: f of a equals f of b. The heights of the graph at the two ends are exactly the same. Conclusion: if all three hypotheses are satisfied, then there exists at least one point C with a less than C less than B such that the derivative at C is 0. F prime of C equals 0. In other words, somewhere between the two equal height ends, the tangent line is horizontal, the graph is momentarily flat. Real-world analogy: imagine a smooth hill that starts and ends at the same elevation like a road that goes up a gentle rise and then comes back down to the same level. Even if the hill is wavy, there must be at least one spot where the slope is flat, a crest or a trough. That flat spot is the C guaranteed by Rolle's theorem. Picture the graph of a function drawn from point A equals a f of a to point B equals b, f of b. The theorem tells us that if A and B lie on the same horizontal line, that is f of a equals f of b, then the curve must somewhere turn back on itself horizontally. Flat spot: horizontal tangent. The line that just touches the curve without cutting through it, the tangent, is horizontal at some interior point C. This is shown as a small dashed line parallel to the x-axis. Why it must happen? Because the curve cannot go from the height at A to the same height at B without either rising above and then falling back or staying flat all the way. In either case, a horizontal tangent appears. Physical picture: think of a roller coaster track that starts and ends at the same height on a segment of track. The car must either go up and then down, or down and then up, before reaching the end. At the very top of a hill or the very bottom of a dip, the car's velocity in the horizontal direction is momentarily 0. That point corresponds to C. Diagram description for mental image: draw a smooth curve from x equals a to x equals b with the same y value at both ends. Mark a point C in the middle where the curve looks like a gentle peak or trough. At C, draw a short horizontal line to represent f prime of C equals 0. Step 1. Use the extreme value theorem, abbreviated as EVT. The extreme value theorem says that a continuous function on a closed interval, a to b, attains a maximum and a minimum. So because f is continuous on a to b, there exist points x max and x min in a to b such that f of x max is greater than or equal to f of x, and f of x min is less than or equal to f of x for all x in a to b. Step 2. Compare with the endpoint condition. Since f of a equals f of b, the maximum and minimum cannot both occur strictly at the endpoints unless the function is constant. Constant function: if f of x equals k for every x, then f prime of x equals 0 everywhere, so any c in a to b works. Maximum inside: if the maximum value occurs at some interior point C in a to b, then by Fermat's theorem, a differentiable interior extremum has 0 derivative, we get f prime of C equals 0. Minimum inside: the same reasoning applies if the minimum occurs inside. Step 3. Conclude. At least one of the interior extreme points must exist, otherwise the function would be constant, which also satisfies the conclusion. Hence there is a C with a less than C less than B such that f prime of C equals 0. Analogy: think of a hiker walking on a trail that starts and ends at the same altitude. The highest or lowest point on the trail must be somewhere in the middle, and at that point the slope of the trail is flat. Exactly what the proof shows using the extreme value theorem. Key mathematical tools used. Extreme value theorem guarantees maximum and minimum on a closed interval. Fermat's theorem says the derivative is 0 at an interior extremum. Continuity is needed for the extreme value theorem, and differentiability is needed for Fermat's theorem. Explanation: verification checklist applying the theorem to a given function. Step 1. Continuity on a to b. Plug the function into a graphing tool or look for any breaks, jumps, or infinite discontinuities between a and b polynomials' signs. Cosines exponentials are always continuous. Step 2. Differentiability on a to b. Ensure the derivative exists for every interior point. Look for sharp corners like absolute value or vertical tangents like square root of x at 0. If the derivative formula is defined for all x in a to b, you are good. Step 3. Equal endpoint values. Compute f of a and f of b. They must be exactly the same number. If they differ, Rolle's theorem does not apply. Step 4. Find a point c with f prime of c equals 0. Differentiate the function, set the derivative equal to 0, solve for c. Inside a to be at least one solution. Must lie strictly between a and b. Step 5. Confirm c lies in the open interval. Verify a less than c less than b if the only solution is at the endpoint. The theorem is not satisfied. If every row in the checklist is ticked, then Rolle's theorem holds for that function on that interval. Quick tip, often the hardest part is step 3, the endpoint equality. Many textbook problems are crafted so that f of a equals f of b holds by construction, like using sine x on 0 to pi, which gives 0 at both ends. Typical function types that satisfy Rolle's conditions: polynomials, trigonometric, etc. Polynomials, for example, x to the n, x cubed minus 3x polynomials are continuous everywhere and differentiable everywhere. By choosing endpoints where the polynomial values match, condition 3 is satisfied. F of x equals x cubed minus 3x on negative square root of 3 to positive square root of 3 gives f of negative square root of 3 equals f of positive square root of 3 equals 0. Trigonometric sine, cosine, tangent were defined. Sine and cosine are continuous and differentiable for all real numbers. Pick intervals of length a multiple of 2 pi, or pi for sine, to get equal endpoint values. F of x equals sine x on 0 to pi gives sine 0 equals sine pi equals 0. Exponential and logarithmic, e to the x natural log of x on the positive domain. Both are smooth, continuous, and differentiable. For exponentials, you need a clever interval. E to the a equals e to the b only if a equals b, so you must use a constant function or combine with other terms. Logarithms can work with a shifted function. F of x equals natural log of x minus natural log of 2 minus x on 0 to 2 gives equal values at the ends. Rational functions, quotients of polynomials. Continuous and differentiable wherever the denominator is not 0. Choose an interval that avoids poles and where the function values match. F of x equals x over x squared plus 1 on negative 1 to positive 1 gives f of negative 1 equals f of 1 equals negative 1/2. Piecewise smooth, different formulas on subintervals. As long as the overall function is continuous at the joining points and differentiable inside each piece, Rolle's theorem can still apply. The verification checklist is crucial here. Bottom line, the theorem cares about behavior on the interval, not about the global class of the function. If the 3 hypotheses hold, any smooth-looking curve, no matter how exotic, will have a horizontal tangent somewhere inside. Real-world analogy. A road that is built from different materials, asphalt, concrete, but is perfectly smooth at the joints, no bumps. If the road starts and ends at the same elevation, there must be a flat spot somewhere, regardless of the material changes. Example problem. Verify Rolle's theorem for f of x equals x cubed minus 3x plus 2 on the interval negative 2 to 2. Step 1. Check continuity. F of x equals x cubed minus 3x plus 2 is a polynomial, so it is continuous everywhere, in particular on the interval negative 2 to 2. Step 2. Check differentiability. The derivative is f prime of x equals 3x squared minus 3, defined for all real x. Hence, f is differentiable on the open interval negative 2 to 2. Step 3. Equal endpoint values. F of negative 2 equals negative 2 cubed minus 3 times negative 2 plus 2 equals negative 8 plus 6 plus 2 equals 0. F of 2 equals 2 cubed minus 3 times 2 plus 2 equals 8 minus 6 plus 2 equals 4. Since f of negative 2 is not equal to f of 2, the third hypothesis fails. Therefore, Rolle's theorem does not apply on the interval negative 2 to 2. What if we choose the correct interval? Notice that f of negative 1 equals negative 1 cubed minus 3 times negative 1 plus 2 equals negative 1 plus 3 plus 2 equals 4, and f of 2 equals 4. So on the interval negative 1 to 2, the endpoints are equal. Verify continuity and differentiability, still true. Solve f prime of c equals 0. 3c squared minus 3 equals 0 implies c squared equals 1 implies c equals plus or minus 1. Only c equals 1 lies in the open interval negative 1 to 2. Hence c equals 1 satisfies f prime of 1 equals 0. Rolle's theorem holds on the interval -1 to 2. Lesson: always start with the equal endpoint test. It can instantly tell you whether the theorem is applicable. Visualization: plot the cubic curve. The graph crosses the x-axis at x equals -2 and x equals 1. Between -1 and 2, the curve starts and ends at the same height y equals 4 and has a flat tangent at x equals 1. F of x equals x squared for a less than or equal to x less than c, and equals 2cx minus c squared for c less than or equal to x less than or equal to b, whereas less than c is less than b. At the joining point x equals c, the left-hand limit is c squared, and the right-hand value is 2c times c minus c squared, which simplifies to c squared, so f is continuous at c. Both pieces are polynomials, so the function is continuous on the whole interval from a to b. The derivative on the left side is 2x, giving a value of 2c at x equals c. The derivative on the right side is the constant 2c since the left and right derivatives agree. F is differentiable at c, and everywhere inside the open interval from a to b. Evaluating the endpoints, we get f of a equals a squared and f of b equals 2cb minus c squared. Rolle's theorem requires these two values to be equal, which gives the condition a squared equals 2cb minus c squared. This is a relationship that must hold among a b and c, otherwise the hypothesis fails. The derivative is piecewise. 2x for x less than c and 2c for x greater than or equal to c. Setting the derivative equal to 0 gives two possibilities. Either 2x equals 0, which yields x equals 0 provided 0 lies between a and c, or 2c equals 0, which means c equals 0, making the right piece flat. Thus, if the parameters satisfy both the endpoint equality condition and the existence of a point where the derivative is 0 as described, Rolle's theorem holds for this function. If either condition is not met, the theorem does not apply. Takeaway for the exam: when a function is defined piecewise, you must verify continuity and differentiability at the breakpoints, in addition to the usual checks on the interval. For example, choose a equals -1, c equals 0, and b equals 1. Then f of -1 equals 1 and f of 1 equals 0, so the endpoint values are unequal and Rolle's theorem fails. Another example: take a equals -1, c equals 1, and b equals 2. Then f of -1 equals 1 and f of 2 equals 3, again unequal, so the theorem does not hold unless the parameters are adjusted to satisfy the equality condition. Imagine a road built in two sections, a gentle hill represented by the quadratic part and a straight incline represented by the linear part. If the road is smooth where the two sections meet and the start and end heights are the same, drivers will encounter a level stretch somewhere, which mirrors the point guaranteed by Rolle's theorem. Frequently asked multiple-choice questions on the necessary conditions of Rolle's theorem. 1. Which of the following is not a required hypothesis for Rolle's theorem? Option A, the function must be continuous on a to be closed interval. Option B, the function must be differentiable on a to be open interval. Option C, the function must satisfy f of a equals f of b. Option D, the function must be monotonic on a to be closed interval. Answer: D. Monotonicity is not required. In fact, a monotone function with equal endpoints would be constant. 2. If f is continuous on a to be closed interval and differentiable on a to be open interval, but f of a not equal f of b, what can we conclude? Option A, there is still guaranteed a point c with f prime of c equals 0. Option B, Rolle's theorem does not apply but the mean value theorem does. Option C, neither Rolle's nor the mean value theorem can be used. Option D, the function must have a maximum at an endpoint. Answer B, without equal endpoints, Rolle's theorem fails, but the mean value theorem, which only needs continuity and differentiability, still holds. 3. Consider the function g of x equals absolute value of x on -1 to 1 closed interval, which hypothesis fails? Option A, continuity on -1 to 1 closed interval. Option B, differentiability on -1 to 1 open interval. Option C, equality g of -1 equals g of 1. Option D, none, all hypotheses are satisfied. Answer B, absolute value of x is not differentiable at x equals 0, a point inside the interval. 4. True or false? If a function satisfies all three hypotheses of Rolle's theorem, then the point c where f prime of c equals 0 is unique. Option A, true. Option B, false. Answer B, the point may not be unique. A flat plateau, for example, f of x equals open parenthesis x minus 1 close parenthesis squared times open parenthesis x minus 2 close parenthesis squared on 1 to 2 closed interval, has infinitely many points where the derivative is 0. 5. Which theorem is a direct generalization of Rolle's theorem? Option A, intermediate value theorem. Option B, fundamental theorem of calculus. Option C, mean value theorem. Option D, L'Hopital's rule. Answer: C. The mean value theorem reduces to Rolle's theorem when f of A equals f of B. How to use these multiple choice questions in study: treat each option as a mini checklist. When you see a new problem, mentally run through the 5 statements: continuity, differentiability, endpoint equality, monotonicity, and uniqueness. This habit quickly tells you whether Rolle's theorem can be invoked. Practical tip: in engineering mathematics, many maximum stress or minimum cost problems require checking these conditions before applying the theorem. The multiple choice questions help you remember the exact checklist.